In our universe, we are finding celestial titans that break and defy our every expectation. Imagine a black hole so powerful that every year it devours the mass of 300 to as many as 3,000 of our suns. A supergiant monster, consuming matter at the fastest rate ever seen by a black hole, born within the first 500 million years after the Big Bang. It hides in silence, billions of light years away. Invisible, except for the immense amount of energy it unleashes. Now imagine that this celestial monster is growing faster than nearly any other black hole we've ever seen. This discovery is shaking the very foundations of astronomy, challenging long-held theories about how black holes form and grow. It sits in a small infant galaxy, hidden behind a group of galaxies called Pandora's cluster. It's so far away that the light reaching us today began its journey when the universe was only about 470 million years old. That means we're seeing one of the earliest known black holes ever detected. And what makes it truly jaw-dropping is that it's already supermassive, with a mass of around 40 million suns. Chandra's X-ray data shows that this black hole is growing at a tremendous rate, feeding on surrounding gas faster than almost any known black hole. When a black hole feeds, the matter falling towards it gets superheated, releasing intense X-rays before crossing the event horizon, the point of no return. These X-rays are what Chandra detects, and the signal coming from UHZ1 is powerful enough to have traveled for more than 13 billion years through space and time to reach us. What's truly shocking is how bright and energetic this black hole appears to be for such an early stage of the universe. It's not just feeding, it's feasting. Scientists estimate that it's gaining the mass of hundreds of suns every year. That may sound comparatively small, but for a black hole that young, it's unbelievably fast. This discovery helps confirm that some black holes may form not from the collapse of stars, but from the direct collapse of enormous gas clouds. Instead of starting small and growing over billions of years, this black hole might have been born already massive, perhaps even up to 100,000 times the mass of our sun, and then continued to grow at an unbelievably intense pace. If that's true, it would explain how supermassive black holes appeared so early in cosmic history. Astronomers use both the James Webb Telescope and Chandra to make this discovery. James Webb first identified the galaxy UHZ1 in infrared light, spotting a faint but clear signature of a very distant and compact galaxy. Chandra then zeroed in on the same spot, detecting strong X-rays, a telltale sign of a feeding black hole. This combination of observations created a cosmic fingerprint, proving that UHZ1 is powered by a black hole growing at a faster rate than we even thought possible. But this creates a huge problem. How is it growing so fast without tearing itself apart? Normally, a black hole's growth is limited by what's called the Eddington limit, a balance between gravity pulling matter in and radiation pushing it back out. As gas falls toward a black hole, it gets heated by friction and releases enormous energy. That energy pushes outward on the surrounding material, effectively limiting how much more gas can fall in. It's like a cosmic speed limit for growth. If a black hole tries to consume faster than the Eddington rate, the radiation should blow away the material that it's trying to consume. Yet, the black hole in UHZ1 appears to be breaking that limit. How is that even possible? One idea is that it's feeding in chaotic bursts, swallowing giant clouds of gas so quickly that the radiation doesn't have time to push back before it's consumed. Another idea is that its accretion disk might be thick and funnel-shaped, allowing radiation to escape through the poles, while more material keeps falling in from the sides. This would let the black hole cheat the Eddington limit and keep growing at a runaway pace. There's also the possibility that it's spinning extremely fast. When a black hole spins, it drags the very fabric of space-time around with it, a process called frame dragging. This could make accretion more efficient and change how radiation escapes, again, letting it grow faster than normal physics would allow. Whatever the explanation, this discovery is monumental because it offers a glimpse into how the first generation of supermassive black holes formed. For decades, astronomers have struggled to explain how black holes could become so massive so soon after the Big Bang. The black hole in UHZ1 might be a missing link, proof that some black holes formed through direct collapse and then experienced a short and furious growth spurt. Naturally, astronomers have begun wondering what this object might look like today, 13.4 billion years later. If it was already 40 million solar masses when the universe was young, how massive could it be today? But black holes don't grow at a constant pace. They depend on the amount of available gas, dust, and stars nearby. Most reach a limit, called the Eddington limit, that controls how fast they can eat. If a black hole feeds right at that limit, its mass can double roughly every 45 million years, a timescale called the Salpeter period. In theory, if UHZ1 had somehow maintained that growth rate since its birth, it would have doubled hundreds of times and become larger than the entire visible universe. Obviously, this is impossible. In reality, its growth slows dramatically once the black hole depletes its surroundings of any gas and nearby objects, or once its own radiation pushes material away. Scientists think that UHZ1's black hole likely fed aggressively for its first few 100 million years before entering a quieter phase. If it doubled its mass every 45 million years for about 500 million years, roughly 11 doubling periods, it could have reached 80 billion solar masses, placing it among the most massive black holes. But even a conservative scenario would place it at billions of solar masses, comparable to some of the largest black holes we've found at the center of galaxies today. If the UHZ1 black hole kept growing at that pace for only a short time, it could still easily be a few billion to as much as 100 billion solar masses. By detecting faint X-rays from the early universe, Chandra allows scientists to peer into cosmic history and see the first structures that formed in our universe. And when its data is combined with the infrared vision of the James Webb Space Telescope, it's like having two superpowers combined into one. It gives the ability to see both the hidden heat of the early universe and the violent energy released by black holes as they feed on nearby matter. The black hole in UHZ1 stands as one of the most extraordinary discoveries of modern astronomy. It's growing at a rate that defies our theories and shows us that the universe was capable of creating supermassive giants from the time it was born.